Hello, pre-calculus class. I wanted to make a really quick video here on just some of the equations and characteristics of polynomial functions that we didn't get to cover in the last few videos. I'm not going to make this long because you can read and probably decode a lot of this on your own, but I wanted to walk through just a couple of things in here in the equation and then in the graphs and interpreting. So um, general equations of polynomial functions, we use these n's, right? N being a positive integer, some whole number, 6, 7, 12, 3, right? No decimals, no negatives allowed, no irrational numbers like pi or square roots. Um, but we use this, and when we don't know the degree, we'll often write it in this form with these subscripts and exponents with like n as this variable, right? So let's do an example, like if this was a fifth degree polynomial function, like n would be 5, right? We call it that n is the degree of the polynomial. We could say it's a polynomial of degree 5, or it's a fifth degree polynomial. And so this I would read as like a sub 5, subscript 5, times x to the fifth. Then the next term would be a sub, well, if n is 5, n minus 1 is 4, so it'd be a sub 4 times x to the fourth. Then it would just continue on down, right? A sub 3, x cubed, and eventually a sub 2, x squared, a sub 1 times x to the first power. When it's to the first, we usually don't write anything. And then finally a sub 0 times x to the 0 if you want to put it there, but anything to the 0 power is just 1, so that last term is always just a 0, right? I have this dash in between here because like if n is a larger number, like, something more than 5 or 6, right, I can fill it in the whole way through, right? Only things, right, these have to be whole numbers, right? And it always ends with a0. We never go into the negatives there. Right, the coefficients have to be real numbers. They can be 0. Sometimes you can have different things, and there's an example down here that says, right, here's a 7th degree polynomial function with a degree 7, and there is no 6th or 5th, like x to the 6th or x to the 5th term. It just comes straight to x to the 4th. So even though there's only 1, 2, 3, 4, 5 things in here, 5 distinct terms, that highest degree is a 7th degree polynomial. The highest exponent is 7, so it's a 7th degree polynomial. Oftentimes, right, just a little quick thing over here, we don't like to use those subscripts. If I don't know what it is, if it's an nth degree polynomial, I'm stuck using subscripts. But if I know, like, hey, this is a 3rd degree polynomial, or it's a cubic function, we usually just start with the letter a and then go alphabetically: x cubed, bx squared, cx, and d. And then we have some characteristics of specific, like, nth degree polynomials that we will have a couple of questions that get at these in section 15.3. An nth degree polynomial can have up to n distinct increasing and decreasing branches and n minus 1 vertices. So what that means is that like a 3rd degree polynomial could have 3 different distinct increasing and decreasing branches, and then 3 minus 2 or 3 minus 1 is 2. It can have 2 vertices. A 6th degree polynomial could have 6 different like increasing and decreasing branches and have up to 5 vertices. Right. So I got an example down here. Here's a cubic function. Right, 3rd degree polynomial. It's got an increasing branch. It hits a vertex up here. Vertex is where it turns around. It has this decreasing branch. It hits a vertex again, and then the final increasing branch. So I have that 3rd degree has 3 distinct branches: one up, one down, one up again, and then 2 vertices where it turns around. Right, so it's a good characteristic, it's a good indicator of like, if you see data that kind of goes up, then down, then up, it shows that, yeah, this should probably be a cubic function of sorts, right? A few other pieces that have to do with the degree of that polynomial is the end behavior. And by end behavior, I mean like what happens as x goes off to the left or goes off to the right. As x goes to positive infinity off to the right, the x values are getting larger, or off to negative infinity. They keep getting infinitely smaller, closer to negative infinity there. If that degree is even, right, the end behavior is going to go in the same direction. So both of these here are odd, right? A 5th degree and a 3rd degree, where the end behavior is going in opposite directions, right? As x goes off to positive infinity, as x increases versus as x decreases, the y values are going in opposite directions. Off to the right, it's going up. It's right. It's getting larger and larger and larger. right? But as it goes off to the left, it's getting smaller and smaller. It's going down. So my end behavior, right? If they're going in opposite directions, if one is going up and the other is going down, I know that it should be an odd degree polynomial function. If I had one that was going in the same direction, say if this like turned around and started to come back up, uh, then that would indicate that it should be an even function or an even degree polynomial function here. Um, and every single polynomial, an nth degree polynomial, will have exactly that many zeros, right? So this cubic function has got 1, 2, 3 zeros where it's crossing the x-intercept. But some of those zeros, as we saw it in the last video, might be complex, right? They might have an imaginary component to them where it would make it 0 if you did some math with imaginary numbers that we haven't really talked about a whole lot. But you can't really see it on the graph. Like this is a 5th degree polynomial function. It has one distinct decreasing branch and another increasing one and then another decreasing one. So it really only has 3 branches here, 3 zeros, 1, 2, 3 that I can see, and 2 vertices, 1, 2. So if I were just to look at like this data, it might look like a cubic function just like this one, but it's a 5th degree, like as I plugged it into Desmos. So you can kind of see there's like a little wobble in the middle here. That kind of would tip you off a little bit, maybe, that it's not a pure, nice, smooth cubic function. There's really some complex zeros kind of somewhere in this range, right? And by that, it doesn't really have a whole lot of meaning because it's not graphically there, but right, there are some complex numbers with imaginary components that would make the value 0 that aren't just these 3 different ones here.